Hello everyone, welcome back to General Relativity for Beginners, episode 2. If you're now here, don't worry, you're in the right place because we are breaking down complex concepts into easy to understand pieces. If you're ready to take your understanding of the universe to a whole new dimension, you are in the right place. In this episode, we are going to unravel the fascinating evolution of special relativity. So why should you stick around and watch this video till the end? Our understanding of the universe has come a long way thanks to the brilliant minds like Galileo, Einstein and Lorentz. In this episode, we will uncover the evolution of special relativity and why it is crucial for our modern understanding of the universe and how it can take us down to the complex calculations which are made easy in this video for general theory of relativity. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to episode 2, General Relativity for Beginners. Well, first let us look into what we called is the evolution of special relativity, because we need to understand first how the special relativity evolved. Now the picture on the left hand side that you see, the photograph, is actually the original cover of Einstein's Special Theory of Relativity. The Annus Mirabilis papers, which are coming from the Latin word Annus Mirabilis, which means miracle year, are the 4 papers that Albert Einstein published in Annalen der Physik or Annals of Physics, a scientific journal, around 1905. So these 4 papers were major contribution to the foundation of modern physics. They revolutionized science's understanding of the fundamental concepts of space, time, mass and energy. The first paper which was explained the photoelectric effect, here you can see, established the energy of the light quanta E equal to hf and was the only specific discovery mentioned in the citation awarding Einstein the Nobel Prize in Physics. The second paper you can see explained Brownian motion, which established the Einstein relation and led reluctant physicists to accept the existence of atoms. The third paper, which we are going to explore, Einstein's theory of special relativity, established the universal constant speed of light c equal to constant and for thereof all the frames of reference and a theory of space-time. The fourth consequence of the theory of special relativity developed the principle of mass-energy equivalence expressed by the world-famous equation E equals to mc square, which led to the discovery and use of atomic energy. From here, when we turn the pages, what we find is that special theory of relativity actually comprises of 2 basic, I would say, postulates. First, it assumes that the laws of physics are invariant or identical in all inertial frames of reference, I mean to say, which have no acceleration, and this led to the unification of space and time into something which is called space-time. The second is that the speed of light in vacuum is the same for all observers regardless of the motion of light source. That means both time and spatial distances are no longer absolute. Now this was actually, I would say, the 2 basic tenets, the 2 basic ideas of special theory of relativity, but the question still remains unanswered, that is how special theory of relativity actually evolved. Now although Isaac Newton based his physics on absolute time and space, he also adhered to the principles, Galileo's principles of relativity, restating it precisely for mechanical system. This can be stated, for example, as far as the laws of mechanics are concerned, all observers in inertial motion are equally privileged and no preferred state of motion can be attributed to any particular inertial observer. However, as to an electromagnetic theory of electrodynamics which was developed during the 19th century, the wave theory of light as a disturbance of a light medium or luminiferous ether was widely accepted. The theory reaching its most developed form in the work of James Clerk Maxwell, and according to Maxwell's theory, during that time all optical and electrical phenomena propagated through that medium which is called the ether, which suggested that it should be possibly I would say, experimentally detectable or determined motion relative to the ether. Now this ether theory has got many stories, many further implications, etc. But we are talking of that time when ether was considered to be a theory which was not yet experimentally proved, but Maxwell's equations and others, even gravity, was thought to propagate through some kind of a medium which is considered as ether. Now the failure of any experiment to detect motion through the ether was actually developed first by Michelson and Morley, and Michelson-Morley experiment actually concerned of two light beams which arrived at the detector, and in order to find out that whether there is an ether or not, it always moved in the same direction, indicating actually that there is no existence of ether. In 1892, Henry Count Lorentz developed the theory of electrodynamics based on an immobile luminiferous ether, physical length contraction, and a local time in which Maxwell's equations retain their form in all inertial frames of reference. That means Lorentz transformation, etc., which we will explore, actually was developed without the presence of ether. Working with Lorentz ethers, here is another French mathematician, Henri Poincaré, having earlier proposed a relativity principle as a general law of nature, including electrodynamics and gravitation. Now, use this principle in 1905 to correct Lorentz transformation. Henri Poincaré transformed formulas resulting to an exact set of equations that are now called as Lorentz transformation. I was reading and going through some historical papers, and I found that just like general theory of relativity has a competition and I would say a dilemma between David Hilbert and Einstein, who published it before, in case of Lorentz transformation special theory of relativity, also there is a controversy that it was Henri Poincaré, whose Poincaré group actually was prior to the formation of Lorentz transformation, and he corrected and used Poincaré group, and later it came to be known as Lorentz transformation. It is very interesting. If you want, you can go ahead and read it. However, a little later in the same year, Albert Einstein published his original papers on special relativity, which again based on the relativity principle, he actually independently derived and radically reinterpreted the Lorentz transformation by changing the fundamental definitions of space and time intervals, while abandoning the absolute simultaneity as proposed by Galilean kinematics, thus avoiding the need for any reference of luminiferous ether in classical electrodynamics. This is the pretext, this is the context in which special theory of relativity actually came into being. This is the evolution, this is the history, starting from ether theory, which actually propagated, people thought that these things propagated, then it was Einstein, Isaac Newton, then it was Galileo, and later Michelson Morley's experiment proved that there is no existence of ether, which was taken up further by Henri Poincaré, Lorentz, and then Albert Einstein. But the question remains that why do we need special theory of relativity? I mean to say, life was good, isn't it, without special relativity? But what was the actual need that special theory of relativity came into being? Coming in the next part of the video. Why do we need special relativity? Let us understand quickly. So we are trying to find out what was the real motivation behind formulating a special relativity. So actually what you see is that the Michelson-Morley experiment is related to special relativity in that it is one of the key pieces of evidence that led Albert Einstein to develop his theory. So Einstein realized that the only way to explain the results of the experiment was to abandon the concept of the ether and to postulate that the speed of the light is constant in all frames of reference. So first one is that electromagnetic theory, James Clerk Maxwell's equations described the behavior of electromagnetic waves and suggested the constancy of the speed of light. However, it was not clear how this consistency with the speed of light reconciled with the classical mechanics and the Galilean relativity. So that was very important, and that is the primary and the first reason of formulating special relativity. The second is that the inconsistency in terms of the Michelson Morley experiment. So it was not clear actually that this consistency would actually lead to the classical mechanics and how it would be united. Also, the Michelson-Morley experiment, which I was stating that the experiment found no detectable motion of the Earth relative to the ether. So that was also that the constancy of the speed of light was being established. The next thing what we find is that there is an amount of inadequacy in terms of Newtonian mechanics, because you see Newtonian mechanics was inconsistent with the behavior of particles or objects moving close or almost to the speed of light. So there was a need, the need of the hour was a new theory which would reconcile with the inadequacy of Newtonian mechanics. Also there was a lack of absolute frame of reference, because Einstein was influenced by the idea that there is no absolute reference frame at rest in the universe, and he posited that all motion is relative and the laws of physics must be considered for all inertial observers. So here you see what we find is that Einstein proposed the theory of special relativity in 1905. It introduced the concepts that would require for the same for all observers. So the lack of absolute frame of reference, inadequacy, inconsistency with electromagnetism, the Michelson-Morley experiment, all these were setting the stage on fire. And what was that fire? That the fire was the world was about to witness a new theory, a special theory of relativity, which would remove these inconsistencies and establish the consistency with the speed of light, the lack of absolute frame of reference, inadequacy in terms of Newtonian mechanics. As far as this part of the video is concerned, we have understood what is the concept, what is the reason, and what are actually the motivational source behind formation of special theory of relativity. But as you can understand now that we are going for a transfer. We are looking for a transformation from the old Newtonian mechanics to a new theory of special relativity, which the world was waiting, and the entire, I would say, gamut and the matrix of science was about to reveal something new. The question is that this transformation was not only required in terms of mental setback, in terms of mental acceptance of a new theory, but also in terms of equation. So the question arises that why do we need those transformation? I mean to say, transforming from Newtonian mechanics to special relativity, first of all, we need to understand that why do we need transformation equations? Coming up in the next part of the video. So first of all, we need to understand that the fundamental laws of physics, for example, Newton's law of motion, are intended to be universal, right? And apply uniformly to all objects and observers. So here is one frame of reference, here is another frame of reference. Now, in order to maintain this universality, we need a way to relate the observers to different observers, even if they are in relative motion. So the first reason is that in order to establish the universality, we need a way, we need a set of equations to relate the observations to different observers, even if they are in relative motion. The second thing is that transformation between frames of reference. For example, consider the motion of this truck, okay, or a vehicle or airplane or spacecraft. Observer in these vehicles need to be describe their own motion, and this description should be consistent with this part of the airplane. So this description should be consistent with the observation from a stationary observer on Earth, moving on airplane or whatsoever. So observer in these vehicles need to describe their own motion. So a transformation was required. Third thing was that to understand the behavior of objects in relative motion, we need a framework because that connects the observations different observer. This is particularly important in scenarios involving moving objects such as celestial objects, particles in accelerators, or behaviors of lights and signals. So that is why we need to understand how the relative motions will move. Now, further, what we find is that, for example, we found that Galilean transformation actually got a new way of transformation to Lorentz transformation. We will soon observe Galilean transformation, the limitations, etc. We also found that from flat space we need an object which are called tensors, exotic objects, which I'm making videos when we transfer and get into a curved space, because we need something which general vectors cannot define. So here is also a need of another transformation. We also see that these Maxwell's equations, once they are made into relativistic equations, then we also need a transformation of equation. How these things will be transformed into relativistic form. In spite of the transformation, the laws of physics will be the same. Also in terms of quantum mechanics, suppose we have a state vector in the spin-up basis. We want to transform this state vector to the spin-down basis, and the unitary matrix that transform within the two bases is given by this. So what is happening out here is that all this would require a transformation not only in terms of mental thought but also in terms of equations. So right now what we are doing is that we are going very fundamental and we are trying to understand why at all we need transformation. Not only this, we need further things. For example, unification of laws. Transformation equation actually ensure that the laws of physics will remain same, but yet transitioning from one space to another. If you look into my videos in tensors, you will find that there are a lot of things which I have talked about regarding tensors, how things are getting transferred. Another important factor is GPS, because GPS satellite requires the transformation equations to convert their own coordinates to Earth-like coordinates. We also need something which is called transformation equations helps to compare observation. As we have just seen in the few seconds back, that one vehicle and the other, the airplane and the truck. So we constantly need in order to compare things. And lastly, what we can also say that there is a versatility. That means transformation equation, when they transfer from one coordinate or one frame of reference to another, can be used in different coordinate system, thereby generalizing and making our system in physics much more rigid. We see that transformation equations are also important because they provide insight into how fundamental quantities, for example time, velocity, whatever, are actually connected with each other. We also find that transformation equations have been tested and they have been confirmed through different types of experiments. And what we see, obviously, the relativistic effect, because transformation equations will finally govern and change special and general relativity using Lorentz equation, Einstein field equation, etc. So from here, what we can finally find out is this one, that transformation equations are very fundamental, I would say, tools in physics. And they ensure the consistency, predictability and versatility in order to understand how the physics or how the physics world is going around. So that we have understood what is the need of transformation equation, that means how things are getting transformed. One thing which particularly is very, very important is that one such transformation, which is, I would say, not a primitive but something which goes along with Newtonian mechanics, is called Galilean transformation. This is the first level of transformation. It is very important before we go into special relativity coming up in the next part of the video. Galilean transformation. Now you see that Galileo Galilei actually resulted into something where if we have one frame of reference, as you can see on the left, which is accelerating on the right hand frame of reference. So if I perform any kind of experiment, any kind of a physical experiment, it would provide the same result in that. That means if I get a result which is equals to x, which will also produce a result which is equal to x. That means Galilean transformation is a kind of a way. It is a kind of a tool which will make life easy if two frames of reference are moving relative to each other. One transformation or one experiment or whatever we do at one frame of reference will produce another. And that is actually what is called this. The laws of physics are the same in all inertial frames of reference, and it allows us to describe and understand how events and objects differently I would say behave differently when observed. So observation was one of the key importance that we need transformation so that we can find out how things are behaving. And this is the significance of Galilean transformations, that they provide way to compare the results of experiments also. Okay, so we go into the most important part, which is I would say understanding mathematically what is called a Galilean transformation. Now you see this is a reference frames, and reference frame I would say is basically a set of axes or coordinate system which a particular observer uses to record events. Now suppose that, okay, so I have defined, so suppose that the origins of the two frames, one is S and there is S prime, and this is moving at a velocity of v, and the origins of the two frames coincide, t equal to t prime equal to 0. So the Galilean transformation actually looks like this, and the Galilean velocity transformation looks like this. But let us remember one thing, these transformations are only correct when we are taking velocities which are far lesser and not moving close to the velocity of light. So this should be a very important part, that we consider Galilean transformation which involves, I would say, velocities less than the speed of light. Okay, so this is as far as the Galilean transformation goes. Now the most important thing is that key concept of special relativity is that of a frame of reference, and a reference frame, as I have defined, is that how can we tell that these type of reference frame actually physically can we experimentally see how Galilean transformation helps up. Let us look into the next part of the video. So imagine that you're sitting over here on a train that is moving at a constant velocity relative to the ground. Now if I throw a ball, this red one, up, then what I will see that from my perspective or from your perspective, the ball travels straight up and down. However, the perspective of an observer who is standing, I would say, yeah, the ball appears straight up and down. Now, however, from the perspective of an observer standing on the ground, here the ball travels in a parabolic arc, something like this. This is because the observer on the ground is moving relative to the train. So the Galilean transformation actually allows us to transform the results of the ball throwing experiment from the train's frame of reference to the observer frames of reference. So here it is. From the perspective of an observer standing on the ground, the ball moves on a parabolic arc. So this is actually the right usage, I would say practical usage of Galilean transformation. So it allows us to compare the results of the experiments, the one standing on the train and another standing relative on the ground, to understand why the ball travels in a parabolic arc from the observer's perspective. So this is, I would say, experimentally what allows to compare and thereby do the results and the the comparisons, the equations, etc. from one frame of reference to another. So transformation, we have understood why we need transformation. Second is that the most primitive which follows Newtonian mechanics is the Galilean transformation, and this actually shows experimentally how we do. But however, there are certain more things very important about Galilean transformation. Let us look into the next part of our video. So these are the two basic assumptions of Galilean transformation. It assumes that the laws of physics are same and space is absolute, meaning that there is a universal frame of reference. Now there is one very important which is called a historical foundation. Now remember that Galilean transformation was actually developed by Galileo, and it plays and still plays a very pivotal role in the development of classical mechanics, because classical mechanics are based on those two assumptions, and there is absolutely no problem in terms of understanding Galilean transformation. And you remember I spoke in other videos that Einstein's field equation or Einstein's special relativity is something which moves close to the speed of light. But do we travel close to the speed of light in general? No. We are applicable to our daily speed. For example, a tram or a bus or an auto rickshaw or a car, anything. So Galilean transformation, remember, it is very relevant to everyday speed, because it continues to be used in many practical applications and also for education purpose, because in terms of education we first take a step into Galilean transformation, then go into Lorentz transformation and things like that. So one thing what I would like to make an appeal to those who are watching this video is that sometimes we tell that no, Galilean transformation has got its limitation, or it is wrong and it was disproved by Lorentz or Albert Einstein further. But we cannot tell as such that a scientific theory or a transformation to be wrong. And I have talked much on this particular topic on this video, which you can say, which you can have a watch, that is, scientific theories, are they right or wrong? Can we just tell them that yes, this scientific theory is right and this scientific theories are wrong? We cannot tell like that. I have talked during a vacation, I made this video, so you can go ahead and watch into my channel in Physics for Students. Very good, I would say. It creates a different kind of an appeal, and we come out of those wrong notions. Suddenly we say Einstein is right, suddenly we say Newton is wrong or Galileo is wrong. We cannot do that. Having said and understood what is the Galilean transformation, why it is important, and what is the context in which the Galilean transformation was formed, now it is the time that we should look into the ether theory, and the ether theory which was disproved by the experiment coming up in the next part of the video, the famous Michelson Morley experiment. We will really look into the experiment, most importantly why it is important, and most important is that how Albert Einstein used Michelson Morley's experiment to frame his special theory of relativity. Sound waves generally they need a medium through which they travel. We know that. In 1864, James Clerk Maxwell actually showed that light is an electromagnetic wave. Therefore, it was assumed that there is an ether through which the light propagates. The ether theory was actually assumed to be everywhere, and it is unaffected by matter. So the ether theory could be used to determine something which is called absolute frame of reference. So it was during that time it was assumed. Now here comes Albert Abraham Michelson, who was a Prussian-born American physicist of Jewish descent, known for his work on measuring the speed of light, particularly the Michelson-Morley experiment. The other person, Edward Williams Morley, was an American scientist known for his precise and accurate measurements of the atomic weight of oxygen. Now the experiment was something like this. The viewer will see, two beams of light which would travel. The arms display the some interference pattern, and if the system is rotated, then the influence of the ether wind, which was taught during that time, should change the time the beams of the light take to travel and the arms. But what was found was that if the system is rotated, then the influence of the ether would change the time, and it would actually change the interference pattern. Now, obviously, we know, I am not going in much details into Michelson Morley's experiment. You can look into any websites, etc. What is found is that the experiment was performed at different times of the day and the year. Now, why it was conducted at different times? Because by conducting the experiment at different times of the day and the year, they ensured that the direction of the Earth's velocity through space, I mean to say its orbital motion, would vary. And if they vary, this variation in the Earth's velocity would theoretically result in different measurements in the ether theory, but it was not done. So here it was found that there was no change in the interference pattern which was expected to be. And that is what was the conclusion of Michelson Morley's experiment, that they did not detect any significant difference in the speed of light. And what was found is that Albert Einstein actually took this result as one of the key, I would say, ingredient, key element, and formed the special theory of relativity. Question is that how? How Einstein took the Michelson Morley experiment of the no detection of ether and formed the postulates, or we can say the basic ideas of special theory of relativity, coming up in the next part of the video. So the first thing, which is that the conclusion was that there is no measurable difference, obviously, in the speed of light in different directions. So the principle of relativity was then formed, because Einstein actually find out through his imagination and his brilliant brain that the laws of physics has to be same for all inertial observers. And it tells that if there is no measurable difference, it is something like if A equals to B and B equals to C, then obviously A has to be equal to C, something like that. The fundamental principles of physics are consistent. So this C, which is the speed of light in the Michelson Morley experiment, it was found that the speed of light is same in directions, and the speed of light is a fundamental constant. And this fundamental constant was taken up by Albert Einstein as one of the cornerstones of his special theory of relativity, and he realized that the only way to explain the I would say the experiment was to abandon the concept of ether, take the speed of light constant, assume the laws of physics are same, and hereby postulate that the speed of light is constant for this reason. So now you see that how Einstein used the Michelson Morley experiment's result or conclusion to make the first principle of relativity, that the laws of physics are the same for all inertial observers. And that is why I always consider that learning history, learning the evolution of thoughts is very important. Now this one which he formed, that the laws of physics are the same, would come later using Henry Kant to Lorentz transformation, which is one of the cornerstones of special relativity. Coming up in the next part of the video, we will take a quick understanding of what is Lorentz transformation using very simple equations. Now here is a schematic diagram. As you can see, suppose again that you see that in the Galilean transformation we took the same thing, that the origins coincide. Say for example t equals to t hash equals to 0, and that at this time there is a burst of light at the origins. I mean to say, you need to imagine, as light travels with speed c in both the frames, right? The light is traveling both c in both the frames at time t in frame s. The wavelength, the wave front of the light would form a sphere. It would form a spherical pulse where the radius would be equal to c times t. Spherical pulse means something like this. You can see the point source and the wave front, and this would form a spherical structure. And the sphere of the radius would obviously will be equal to the speed of light multiplied by the number by time, so r equals to ct. And for example, this is for the prime frame of reference, and this is for the unprime, and this is for the prime frame of reference, that r prime is equal to c prime and t prime. Now what we get from here, okay, this is another clear, I would say, description of the photograph of the illustration. So from where obviously we would get this one, r equals to square root, which would equal to ct, and from here it will imply obviously this one. And similarly we will get this one, which is for the prime frame of reference. So for the prime we got x squared plus y squared plus z squared, and here we got x prime squared, y prime squared, similar. And now what we see is that this underline these two equations, we wish to start and get a kind of a transformation. So what we do is that we are trying to find a transformation. You have understood what is the reason. Now we are trying to find a transformation, and we would do that transformation with nothing other than Galilean transformation. So here is I would say a set of equations. You can see the Galilean transformation, and here is the Lorentz transformation, or the transformation that we are doing, and we are just substituting this value to this value to this value to of z to this, and t to t, right? We just substituted its value, and what we get is this one. Now you see this one does not match with this one which we just saw. So what is the solution if it doesn't match us? Let us look next. So instead of t equals to, I would say, this one, t prime equals to t, which does not agree, we will try with something like this. T prime is equals to t plus fx, where we consider f to be for some kind of a constant. And if I put this value over here, we will get simply this. Okay, so instead of c square, the earlier equation, okay, let me go back to this one. Yeah, so c square t square, here you see this t square is substituted by t plus fx, and I have just, in a similar way, I have just opened a simple algebra. And here we note that if, okay, so we have written this one again. Okay, so what we see from here, if we put f equals to, I'm just substituting. If I put f equals to equals to minus v times c square over here. Okay, so what I'm doing is that I'm putting this value over here, and what I get from here is that these two values get cancelled out. Okay, so we note that the term minus 2xvt on the left hand side cancels out with this one 2tfx term if we substitute f equals to minus v by c square, and hence what we can say, these two things will cancel out. I have not shown because otherwise the equation would be too long. You can do it on yourself. So earlier what we have done, we have taken t prime equal to t plus fx. Now what we are doing is that we are taking t prime equal to t minus same fx, but I would put this one as this, right? F equals to minus v by c square, and from here this would be the result. Just a second. Yeah, so it would be this. So we now, instead of t prime equal to t plus fx, I will take t prime is equal to t minus fx, and as because f equals to minus v by c square, if I substitute this, t prime will be how much? T minus, and we put v on the top, x is already there, and c square will come at the below. right? So from here we get this. Now let us look into the let us solve it out. So once we solve it, we get the value as this, and then we get a C4 at the bottom, and the C square, and these things will cancel out, and finally we get to here. Now remember, these two terms which we see, we can remove these two terms because it looks quite big by altering the transformation. What do we mean by altering the transformation? This is just this. So we just altered the transformation and we got it. Now here is a catch. The catch is that we will consider another element, for example beta equals to V by C. What is this? This is actually, if you see, it is the ratio of the velocity of an object V compared to that of the light C, and it is dimensionless quantity, obviously. So for objects which are moving slowly compared to the speed of light, that is V by C is a very small number, remember, and as the velocity of an object goes faster and faster and faster, V by C obviously will approach infinity. Okay, so we find beta equal to V by C, and gamma would be 1 by this one, beta by 1. So we can also write it as this, or we can write the Lorentz transformation as this. Both of them are same. I mean to say, you will find either this or this. Now in Lorentz transformation, this one gamma is actually the Lorentz factor. I will explain to you. This is the Lorentz factor. Now what you see, that in Lorentz transformation, t x y z and t prime x prime y prime and z prime are actually the coordinates of an event in two frames of reference, right, with the origins coinciding at t equals to t prime equals to 0, where the prime frame is seen from the unprimed frame as moving with the speed of v along the x-axis. So this is a linear transformation from a coordinate frame in a space-time to another that moves at a constant velocity relative to 1. So you see the unprimed frame as moving with speed along the x-axis. So the Lorentz factor, what it is, let us quickly find out. This origins coincide. Now most importantly, we need to find out that this Lorentz factor has got a very striking feature. Certain things determine, let us look in the next part of the video. So this is the Lorentz factor, and it actually expresses how much the measurements of time, length and other physical properties change for an object while that object is moving. Moving when? Moving when it is close to the speed of light. Remember, we are using Lorentz transformation only when objects are accelerating close to the speed of light. So it actually is an important factor in calculating time dilation, length contraction, mass energy equivalence and constancy of speed of light. So what we say from here is that this is a fundamental and crucial concept in Einstein's theory of special relativity. This is very central. Now that we understand what is actually Lorentz transformation, can we have a kind of a, I won't say limitation, a kind of an understanding between Galilean and Lorentz transformation. So you see, Galilean transformation is classical, which pertains to the theories of Newtonian mechanics, and it is valid for very low speeds. Compared to that of Lorentz transformation is valid for all speeds. Let us look quickly into a tabular structure to make things clear. So here it is. The validity, low speeds, all speeds, time, absolute, relative, length, absolute and contracted, mass is absolute but it will increase, speed of light different from different observer, and obviously it is same for all observers. So this actually gives you a kind of a comparison between Galilean transformation and Lorentz transformation. Nothing is wrong, but it has their own limitation in their own speed and own frames of reference. Few important points on Lorentz transformation is still remaining. First of all, when we take beta equal to V by C, an equivalent transformation can also be this. So this is also noteworthy. Now also, frames of reference can be divided into two groups, inertial and non-inertial frames. So inertial means relative motion with constant velocity, and non-inertial accelerating, moving, curved paths, etc. So the term Lorentz transformation only actually refers to what is called transformation between inertial frames, usually in the context of special relativity. Now in each reference frame, remember that there is an observer, and an observer can use a local coordinate system, which is called a Cartesian coordinate system, using a rod for measuring and a clock to measure a time interval. This is the observer. An event is called something that happens at a point in space at an instant time, or we can say formally a point in space time. So the transformations actually connect the space and time coordinates of an event, as measured by an observer in each frame. So actually the Lorentz transformation, if you look into it, explain how the speed of light was observed to be independent of the frame of reference, and Galilean transformation is something of Newtonian physics and assumes absolute space and time. Obviously this is quite a remarkable difference. However, there are some confusions which I see among students regarding the notation. So this can be written as this, I mean to say both of them are the same. Also, it is worth noting that V should be this and Y will be gamma would be approximately 1. And these can be reduced when they go for a very low speed. These are actually traces back and goes back to the Galilean transformations. So here is my video which contains a lot of, and these days a lot of students are watching and finding it good and got a good number of views, that there is a lot of examination questions regarding length, contraction, muon, decay, etc. in a special relativity, because special relativity comes in the first year, so you can have a look into this. This is something which is related to question and answer, which will help you maybe something related to examination. Now we have talked about Lorentz transformation and how things go, what are the equations that happens, how we remove them, how Galilean and Lorentz transformations is different. One important consequence of special relativity which is calculated by Lorentz transformation is called length contraction. And we will look into very simple equations, what is actually length contraction and how we can measure it. So we will more or less use the same thing, S and S prime. So and we will take that the S and S prime actually is moving away from S with a velocity V along the path axis of X. So let there be a rod, as I mentioned here, L0 in the S frame of reference, and we will call it L in terms of the S prime frame of reference. So this rod is actually at rest with respect to S, but moving relative to the other frame, that is S prime. So what we say is that L0 obviously will be equal to what? X2 minus X1. So this is the S prime frame of reference, and from here in S prime frame of reference, which is just now highlighted, this one, the length of L of the rod of the distance between X prime 1 and X prime 2 would be recorded at this time. Very simple, T1 prime equal to T2 prime, T prime 1, T prime 2 and T prime. And using the Lorentz transformation we can find out this one, and with some easy equations which you can easily do, we can get to this one, and finally we get this. And this one, what we get here, this L0, this is actually the Lorentz factor. So from here what we find is that we go to a kind of a I would like to show you a visual demonstration, although it is not correct. So as the object moves further and gets a velocity, so you can see the length actually contracts. And what is this equation is all about? This is actually the length measurement observer at rest relative to the object measured. This is actually what we call the length measurement to observer moving relative. This obviously is the relative speed, very important for the observer, and this one obviously is the speed of light. Now we understood the Lorentz transformation actually helps us to measure what is called length contraction. We have seen a kind of a partial but not entirely wrong visual demonstration of how a length contracts. But there are certain important factors, I would say, which impacts other areas of physics when we learn length contraction. Let us look into the next part of the video. So what we can tell from now is that length contraction is, in special relativity, is actually a phenomena for an object that is in motion relative to an observer in the direction motion compared to its length as measured its own frame of reference. The first implication, which is very, very important, is that it means what? It means that space-time is absolutely not absolute, and rather a fabric that is woven by the presence of mass and energy, which becomes very evident in general theory of relativity. Also, the relative nature of length it underscores the principle that physical measurements depend on the observer's frame. So in special relativity, there is nothing called absolute length. I mean to say, these are actually what I would say implications, or these are important to know that how length contraction affects the phenomena. Also, there is something which is called time dilation, which we will look into the next part of the video. So it is closely related, because an object speed increases, the time appears to move more slowly. So this is also something which is very important. Now there is relativistic speed limits, because length contraction implies that as an object speed approaches the speed of light, its length in the direction of motion approaches zero. Now this is a key feature of special relativity. Why? Because it can lead to the notions of no massive object, that no massive object can be accelerated to or beyond the speed of light. It sets a kind of a limit. Also, you see, length contraction has been experimentally confirmed through a variety of experiments, including those involving high-speed particles in particle physics. Also, there is these GPS satellites, because the length contraction actually causes the GPS satellites to lose certain length, and this effect was not taken into account. If you don't, then the GPS would not be accurately able to detect the positions on Earth. And the last one, that for objects and vehicles traveling at significant fractions at the speed of light, length contraction has practical implication. For spacecraft, for example, would experience length contraction as they approach relativistic speeds, affecting the physical dimensions of the spacecraft and the distance between the objects which are on board. So these are the implications, very important to understand how things are getting affected, and how length contraction actually helps us to understand physics better. So we are talking about length contraction, which is also related to something which is called, very important, which is called time dilation. Let us look quickly, very simple equation which will explore time dilation, coming in the next part of the video. So consider two frames as before, and an event occurring at x0 at times t1 and t2. So what we find from here, that the time interval between these two events is known, what is called, this one S prime, it is called the proper time, right? This is known as the proper time interval. Now if you're wondering what is proper time, this is a clear definition. So proper time is the time that an observer actually measures an event occurring their frame of reference. And proper time is the only time which is invariant under Lorentz transformation. So this is the definition of proper time. So if in S prime, if we use the Lorentz time, then we get to this one, right? And from here we get into this one. We subtract this one to by Vx0, and then we get this, and from here we get this one. T2 is equal to Vx0 by c square, and from here we get this one, tau equals to gamma t0. So now what is this? This is actually happening all in S prime. This tau is called actually the time dilation factor. I mean to say, this is the time dilation. So the time interval is actually measured in S prime. Check into the equations. I think this one Vx0, and then it's come, yeah, I think this is perfect, right? So this is what actually time dilation does. Don't worry, there are many examples, equations, derivation, which I have avoided because the main idea is general theory of relativity. So obviously time dilation, these things will come into account. Now these are all equations, but can we see this in terms of an illustrative example? Let us look into the next part of the video. So this is the famous twin paradox. So both of the twins start a trip, and the ship travels at a relativistic speed. And when the ship comes back, here you can see the person on the earth is bending down, because at the end of the trip the earthbound twin has aged more. The reason is that because it travels at relativistic speed, time travels slower, so he is actually remains younger. Obviously I have not drawn this. This is the citation. I have taken this from this website. So I was talking regarding some specific notations which sometimes comes to confusion. So regarding the notation, here you see that this is the most common notation. However, this can be also written as this or t prime, etc. So actually what I'm trying to do is that this actually depends on which notation or what you are actually taking. The question rises that time dilation, again, how does it impact the nature of physics, or what are the implications of that? Let us find in the next part of the video. So you see, time dilation actually is a fundamental consequence of special relativity. So first we see that the relative nature of time becomes very evident, because time dilation underscores the relative nature of time itself, and it demonstrates that time is not an absolute quantity but as observed by different people. We have already seen twin paradox, the famous one. There are a lot of mathematical examination papers setting on twin paradox, etc. also, which you can later look into this. Particle physics also, time dilation is crucial, because there are certain subatomic particles at LHC. When they are traveling close to the speed of light, it impacts the lifetimes unstable. These atoms particles become unstable, and making it possible for observed particles that would otherwise decay before reaching a detector. So particle physics actually has a great many impact in terms of time dilation. Also, you see, we measure the relative velocity as v. So the speed of the moving object relative to the observer plays a very important role. This is the equation. We have already seen what is the Lorentz factor. Obviously, it is a very crucial factor in time dilation. We also have seen what is called a proper time, measured either by tau or delta, doesn't matter. So this is the shortest possible time between events. And again, just like length contraction, this is something which has been experimentally verified. Moon, decay, etc. Lot many examples you can find in the internet. So this actually produces the time dilation, the impact on physics, etc. So that's it, and I think that it is required that we should do a quick summary, isn't it, to find out what we have learned today. So from today's lecture we can say these things. We understood the evolution of special relativity, a little bit of history, the real reason, the motivation why special relativity came, and what were the limitations of the classical mechanics. And why do we need transformation equations? We have seen that the Galilean transformation later went into Lorentz transformation, the foundations of Michelson Morley experiment, and how Michelson Morley experiment helped Einstein to postulate these special relativity, the difference between Lorentz and Galilean transformation, time dilation and its it should be implications, and length contraction and its implications. What is very important for today's lecture is that knowing the real reason why special relativity is born, without knowing that, we cannot go forward to understand general relativity. So that's it for today's video. I would like to thank immensely for you for taking your time to watch this video particularly. Please hit on the subscribe button if you have liked this video, and click on the bell icon to get all the notification from Physics for Student. This is my email ID which you can check in, and this is my other channel of General Theory of Relativity, which you can follow on Facebook, LinkedIn, Instagram and Twitter account. So Physics for Students will continue making and explaining to you videos related to special theory of special relativity, general relativity and so on, and other, I would say, physics and mathematics videos, and whatever the things which are coming on. I think you're enjoying. I would wait for your comments. We'll be soon back with the third episode of General Theory of Relativity, which has just started. Thank you very much for watching this video.